Hi scholars, today we are moving on to the second part of lesson 6. We are going to continue on what we learned yesterday about electric fields and the influences on charges. So for today, you are going to need your notebook and a pen and pencil. And then in terms of tabs open, you should have both today and yesterday's classwork document open. The reason why is because we will be referring to yesterday's classwork in order to answer today's exit ticket. Since both lessons are connected, we can't forget what we learned yesterday. You also should have your Google Classroom open, and then in your classwork document, there's a link to a PhET simulation. You can open that as well if you'd like, so you can play around with the PhET simulation as well. I am going to be doing some modeling with it later. All right, so we are going to continue our exploration on electric fields by watching a quick video. Then we're going to do a PhET simulation demo. Then I'll do some quick explanation. Then you'll do a short reading, a check for understanding, and then our exit ticket to complete the day. So just as yesterday, our guiding questions are: how are electric fields related to electric force? And how can we determine the potential energy a point charge has related to its position? All right, so we're going to start today by watching the video. So as we're playing the video, make sure to take notes on any important and key points. You should take these notes in your classwork document.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 27. It's on electric field strength. And before we start talking about that, I'm going to show you a quick simulation. I'm going to add some charges to a box. And the first time I add those charges, I'm going to add 1 Coulomb charges. And we're just going to watch their behavior. So each of these particles has a 1 Coulomb charge. You can see that they're pushing on each other. Now let's increase the charge to 2 coulombs. And you should be able to realize that there are bigger fields being generated, a greater electric field strength. Now we've got a 3 Coulomb charge. They're really pushing on each other. You might have figured out that these are positive charges because the fields are moving away from the charge. And now if we get a 5 Coulomb charge, they're really applying a force to each other. There's a huge electric field strength, and this one charge can't even find a place to sit. And so if we take an object, we can measure the electric field strength, and we usually represent that using arrows. And so this object has no charge, but if I add a charge to it, it's going to have an electric field charge, or electric field that's moving out from that positive charge. So if I remove the charge, then I remove that electric field. What's going to happen if I add a negative charge? Well, we're going to have the same size of arrows, but now they're pointed towards the charge by convention. If I remove the charge, what happens? They go away. Now this video is about electric field strength. And so if I add 1 charge, get an idea of how long these arrows are, but now let me add 1 more charge, and what happens is we've increased that electric field strength. And if I add another charge, what happens? Again, we're increasing the electric field strength. It's getting larger. And sometimes it's unwieldy to just increase the size of those. So instead what we'll do is as we add more charges, we just add more arrows. And this will be important when we're looking at, for example, 2 charged plates. And so we could represent...
Sorry, I'm just going to stop here really quick. So the point is that the more arrows there are, the stronger the electrical force is, because the more charge there is.
The electric field strength as arrows, and as we add charge, we're increasing the number of those arrows. And so there's a direct relationship between the charge of those plates and the electric field strength. Now it's not always perpendicular, but we're just going to assume that these charged plates are infinitely long. And so in this video, we're really just trying to look at one thing, and that's the relationship between the amount of charge and the electric field strength. And so now I'm going to use a PHET simulation to look at how the amount of charge affects the electric field strength. And we're going to use these electric field strength testers around the outside, and I'm just going to place charges right there in the middle. It's a PHET simulation. I'd encourage you to play around with it. I'll put a link down below. So watch what happens when I add a positive charge in the middle. We've generated an electric field, and as I increase the amount of charge, watch what happens to the electric field strength. It's increasing. There's a direct relationship between the two. And as I pull those charges out, you can see that that electric field strength is going to 0. What happens if we put a negative charge in the middle? You can see that we now have an electric field, but those field lines are pointing towards the charge. As I increase the number of charges, I'm increasing the electric field strength. As I get rid of them, then the electric field strength is going away. But the neat thing about the simulation is you can make it quantitative. So
we're going to stop our video here. So I just want to reiterate a point that he was putting charges in the middle, but these points here are not other charges. They're just indicators of what the electric field looks like. And so let's explore this.
So I'm going to add.
Let's explore this a little bit more. So I just want to name something that I think it was mentioned yesterday, that electric fields are a way for us to model how the electric force of a charge is going to affect another neighboring charge. So let's look at this FET simulation that's going to help us model what this looks like. Right? So as I am, I'm going to ask you guys to draw a few of these things in your notes. Right? So here I have a positive charge that I just placed into the screen here. And I see now that there's lines that are emanating out of my charge. These lines here are a model of the electric field. So it tells me that if I were to place any other charge around this one, then it's going to experience a force because of these fields. So there's going to be some sort of interaction happening here. And so let's do one thing at a time. So here are the electric field lines for one positive charge. Okay. I'm going to remove this guy. So let's put a negative here. So we see basically the same situation, except for the difference now is that the arrows are pointing towards the center of the negative charge. So as a convention, negative electric field lines point towards the negative charge, and then positive the field lines for a positive charge point away. So before we explore what just happened there, let's take a look at our sensor. So this sensor measures the electric field strength. So the closer we're seeing here that the closer I get to my charge, the bigger the vector gets, right? So the bigger the electric field becomes. So what that means is that the closer I get to my charge, the more force I will experience if this thing was to be a charge. I remember this is just a sensor, right? And then the further away we go, the less, the weaker the electric field is. Right? So let's look at what happens when I put a positive charge here. So we see now that these lines are emanating like towards the left over here, but in the area where between the positive and the negative charge, the arrows are pointing towards each other. So that is an indicator for me that there is some sort of attractive force happening, right? So my sensor here tells me that in the middle, there is a really strong electric field, and it would be causing my two particles to get closer and closer to each other. Right, just like we, so they would be getting closer and closer because we know that a positive and negative would be attracting. And then again, the further away I go, the weaker my electric field becomes. So now what happens when I have two equal charges next to each other? So I'm going to put a negative charge here. We know that these are supposed to repel, so what are the electric field lines going to look like in a situation where two charges are repelling? Now, the arrows, I'm going to separate these guys a little bit more so it becomes a little clearer. All right, there you go. So now here I have, I'm going to move my probe around. So as I expect, the closer I get to my charge, the larger electric field strength is. There's this funny thing that happens here in the middle where you have with two electric charges that are the same charge. You see here my probe, there's no arrow pointing out of it. That tells me that here in the middle there's 0 electric field strength. So because these two guys are repelling from each other, directly in the middle, there is no force. Right there, there's no electric field lines in the middle of two charges that are being repelled. And we're going to look in a second a few more diagrams of what that looks like, so it becomes a little clearer to us. Right. Again, this link is, this simulation is linked in your classwork document. If you would like to play around with it more, you can add more charges around and see what the electric field looks like with different configurations. Okay, so let's move on, moving along. So this is what I'd like you guys to draw in your notebooks. This is the electric fields of two individual point charges, meaning one positive charge, the arrows go out, and then a negative charge, the arrows go in. Right, so take the next minute to draw both of these into your notes. When you're ready to come back, hit play. Press pause now. Okay, let's move along. So this is what the electric field looks like for the other two configurations that we saw in the PhET simulation. So here we have a positive and negative charged object, and we see that just like in the demo, the arrows, the electric field lines come out of a charge and of a positive charge and go into a negative charge. So that's always going to be the same convention that all scientists use. And so this is for two charges that are attracting each other. The field lines connect, creating like a force field that connects the two. In the case for the two negatively charged objects on this side, the charges will be repelled, so they can't come close together, and the field lines don't ever connect. So that gives us a visual that those are repelling forces. Okay, and then just as we saw in the simulation, right here in the middle, there's no lines. So the fact that there's no lines here tells me that there is no electric field strength. Okay, moving along to a few key points about electric fields. So electric field lines represent the strength of the force and the direction that the force will act. The more lines, the stronger the electric field. The less lines, the weaker the electric field. Right, and the electric field lines go out radially in all directions. What that means is that they go out, to go out radially means that it goes out equally in every single direction like that, like in a circle. Okay. All right, so now we are going to take the next 6 minutes to read and annotate the reading section in your classwork document. Right. Once you are done reading and highlighting and making comments in your classwork document, you can come back and press play on our video. Press pause now. Okay, scholars, welcome back. Now let's do a quick check for understanding. So using the formula that was revealed in your reading, and also what we know about the electric fields that we saw before, let's compare the strength between this point, let's call this E1, and then this is E2. And then for each one, which one's greater? So we have two different scenarios here. We have this question A and question B. So where is the electric field strength going to be greater? At point E1 or at point E2? Take the next 2 minutes to answer this question in your classwork document. When you are ready to come back, press play so we can go over the answers together. Press pause now. All right, welcome back, scholars. So let us go over our answers. So you might have said that you could have said either that the electric field here is greater, that it's equal to the 182, or it's less than the 182. So based on our diagrams, let's check to see what this would look like. I'm going to draw some field lines here. Just know that you're not expected to know how to do this. I'm just adding them so that it's helpful to visualize what's going on. So for this positive charge, we have two positive charges that are next to each other. So are these guys repelling or attracting? Right, they're repelling, you're right. So because they're repelling, that means that the field lines are going to look like something like this. Ooh. Being very crude here with my drawings, but you guys, hopefully you get the idea. So this looks similar to when we have the two repelling forces, negative charges next to each other. So this is what my field would look like. So what this tells me is that at this point here in the middle, there's actually no electric charge, no electric field lines. So my electric field line is going to be less than whatever's out here, because at this point there's 0 electric fields. And then over here, there will be some sort of electric field strength because there are electric field lines going out next to it. Okay. What about over here? Here now we have a positive charge and a negative charge. In this case, both of them are, they're attracting each other. And because they're attracting, we know that based on what we saw before, the electric field lines are going to connect. I'm going to do something like this. Again, you're not expected to know how these lines would look like. You could have figured out the answer by looking at the previous diagrams that we had in this slide. Right, so here the electric field is going to be stronger in the middle because there's going to be more electric field lines connecting here than there is going to be over on the outside. And that is true because at this point, 1 is directly in the middle between the attraction, so there will be a greater force than there is, greater field than there is over here on this side. So my electric field in the center is going to be greater than the electric field over here at point 2. If you have any questions about this, take a note of them. You can ask your teacher later on. Alrighty, moving along. So a key point that connects our check for understanding with the reading that we just did is that the electric field intensity measures the force a source electric charge places on a point charge in the space surrounding it. And it's measured by the following equation. All right, so please take the next minute or so to write this into your notebook. You can press pause until you're ready to come back. Okay, scholars, welcome back. Let us carry on with our exit ticket. So this is where we're going to need yesterday's reading. So our exit ticket is asking us, how can we determine the potential energy a point charge has related to its position? So remember to refer to your diagrams from yesterday and also connecting it to electric position within an electric field that we learned from today's lesson. Okay, that's all. Once you're done with your exit ticket, that will be all for today. Make sure that you submit your classwork document by the end of the lesson. And if you have any other questions, make sure you address these to your teacher. I hope you have a wonderful day and take care, everyone.